Hi, Math 206. We are entering our final section in chapter 12 on similar triangles, and this is what I think is the most useful section in this chapter because we use similar triangles to construct larger objects and also to create drawings like architectural drawings and to take indirect measurements. So it's super useful. First of all, what are similar triangles? So two triangles are similar if they have the same shape, and we use a tilde to show similar. Okay, if they have the same shape, but not necessarily the same size. All right, so what we, in order to define that, to say the same shape, we want to preserve all the angles. So we say all angles are congruent and all sides proportional. So let me show you what I mean by sides being proportional. Suppose I have one triangle, A, B, C, and another triangle looks like it has all the same angles, but a different size. In order for the sides to be proportional, then the length AB divided by, say, AC has to be the same proportion for the corresponding sides, or the same ratio for the corresponding sides on the other triangle. So A prime B prime over A prime C prime. And this has to be true for all the sides. So I can also say that like BC over AC has to be equal to B prime C prime over A prime C prime. And then you could make the third proportion as well. That AB over BC should be equal to A prime B prime over B prime C prime. So all the sides have to be in proportion. And two polygons that have the same number of vertices, they're going to be called similar if there's a one-to-one correspondence between the vertices of one and the vertices of another, so that the interior angles are all exactly the same and all the corresponding sides are proportional. All right, so just like we had congruence conditions for triangles, we'll have similarity conditions for triangles as well. And then everything for triangles will be used to show similarity for larger shapes because other polygons can be just subdivided into triangles anyway. All right, so the good news is we don't have to show all of these equivalences for every triangle just to know if they're similar. It's actually enough if you know that all of the sides of one triangle are proportional to all the sides of another. So that's called side similarity. Then you don't even have to check the angles. The angles kind of come for free. Also, if in two triangles, two sides are proportional and the included angles are congruent, so this is called side angle side congruence, or side angle side similarity. Then you get for free that the other two angles have to be congruent to each other, and that all the sides are in proportion. And the last one is angle. If two angles from one triangle are congruent to two angles of a second triangle, then you know for sure that the third angles have to be congruent and you get all the sides in proportion for free. All right, so let's find a one-to-one correspondence. Let's do these examples among the vertices of each pair so that the corresponding angles are congruent, and then we'll write the proportions for all the sides, okay? So I know that angle A is congruent to D, B is congruent to E, C is congruent to F. So I would make sure to write triangle ABC is similar to triangle, and I'd make sure to write the vertices in the same order. So this would be D, E, F. All right, and by angle, then you get that the sides are proportional for free. So you can say side length AB over AC equals DE over DF. And also AB over BC, AB over BC has to be equal to DE over EF. And the last one, AC over BC, has to be equal to DF over EF. Just making sure that we're pairing up all the corresponding vertices. All right, and over here, I've got two right angles. So the right angle in DCE is congruent to the right angle in DBA, and angle E is congruent to angle A, and they share angle D, so this one kind of comes along for free, right? So I can say that triangle, say CDE, is similar to triangle BDA. And let's write down all of the proportional sides. We'll say DC over DE is equal to DB over DA. Also, DC over CE is equal to DB over BA. And the last equivalence, or the last proportion, is that DE over CE is equal to DA over BA. So convince yourself that all of the corresponding vertices are in corresponding positions. All right, so this is helpful for us. Let's now see if we can spot similar triangles when we see them, and then we should be able to state why the triangles are similar. All right, so in this example, the AE is parallel to BD, so that information is given to us. So I don't know anything about the side lengths, but I do know some information about angles. If these two lines are parallel, then these corresponding angles here made by the parallel lines and the transversal, they have to be congruent. Same thing over here, you've got two parallel lines and a transversal. That makes these two corresponding angles. So two angles in one triangle are congruent to two angles in another. So by angle, we have that triangle, I'll call this one CBD, is similar to triangle CAE. All right, let's look at this one. BD intersects AE at point C. So what do I know? I'm given here two 90-degree angles, and I don't know anything about the side lengths, but I do know that these two angles, these are vertical angles, and they must be congruent. So I can say by angle, triangle ABC is similar to triangle, I'll start with E, then D, C. All right, well, let's check this one. Here I have one side length, and I'm given that these two triangles are similar, and I'm trying to solve for X here. So what I know is, of course, all the angles are congruent, and also the sides are proportional to each other. So this side, the ratio of side 8 to side X should be equal to the ratio of side length 5 to this side BC. Now I don't have a number for this side. However, I know that the sum of these two sides, this has to add up to 12. And if I call this side length x, then what's remaining is 12 take away x. All right, so let me write down the proportion. So the ratio 12 minus x to 5 should be the same as the ratio of x to 8. And now I can solve for x. So with proportions, there's a quick shortcut for solving. A proportion is a statement that two ratios or two fractions are equal to each other. So there's a quick way to do this, and it's sometimes referred to as cross multiplying, although I don't really like that term because people use it for all sorts of things that aren't really, it's not really cross multiplying. But you do multiply both sides by this denominator, 8, and that will cancel these 8s for you. Multiply both sides by 5, and that'll cancel that denominator for you. So in effect, what you've done is you've taken the denominator here, 8, and multiplied it by 12 minus x, this numerator. So 8 times 12 minus x equals, and then 5 times x. So that's the shortcut, is just to like 8 this denominator times that denominator, or that numerator, and then this denominator times that numerator. And it's just because when you multiply both sides by that denominator, it's just the shortcut for how it works out. Anyways, so let's go ahead and solve for x now. This is an algebra problem. 8 distribute in the 8. 8 times 12 is 96 minus 8x equals 5x. Let me go ahead and add 8x to both sides. I get 96 equals 13x. So divide by 13. We get x equals 96 over 13, which is some decimal. .38-ish. So you can leave it as a fraction, or you can say x is approximately 7.38, or however many digits you want to round to. All right, and this will be the most useful thing for us in applications, is if we know we have similar triangles, then we can go ahead and solve for the height or the distance or the length.